is section 2.2.4, the curl of the electric field. Let's go ahead and assume that we have a point particle at the origin of our coordinate system, and we know that the electric field of that point particle is 1 over 4 pi epsilon naught q over r squared, pointed in the r hat direction. If we were to draw field lines for this point particle, we know that this would be radially outwards. Now assume that I want to traverse some path. Let's go from point A to point B within this field, and we can take whatever route we want. And I want to calculate the total of this path from A to B of the electric field dotted with my path, where dl is just some infinitesimal length along my path. Okay. I can choose to write my infinitesimal displacement dl in spherical coordinates, just basically to match the fact that my electric field is in spherical coordinates, as some infinitesimal displacement in the r hat direction plus r d theta in the theta hat plus r sine theta d phi in the phi hat. So when I take this dot product, I have something with the r hat direction dotted with all of this, and it really only keeps the r hat direction. So that becomes from A to B 1 over 4 pi epsilon naught q over r squared dr. All right, so we can evaluate the integral for arbitrary positions A and B. I do that integral, I get a negative sign, negative 1 over 4 pi epsilon naught. I get a q over r evaluated at positions A and B, which becomes 1 over 4 pi epsilon naught q over RA minus q over RB. All right, where I've put that minus sign back in and switched the order of those integrands to match the book. Okay, so that is the total path integral. Well, I guess haven't said that yet. That is the path integral from E dl from point A to point B. Okay, now let's imagine that we've chosen a path such that I traverse this space from A to B, except I'm going to set B to be at the same position as A. If that's true, then RA is equal to RB, those are the same positions, and I have a closed integral along my path, and that equals 0. And if we apply Stokes' theorem, we can convert this path integral into a curl, and that tells us that the curl of our electric field is equal to 0. All right, and that's consistent with the drawing we had above. All right, this point particle here, all of the arrows are radially outward. There are no curling vectors. This field does not curl. And we have an electric field that has no curl. All right. This is done for a point particle, but this is generally valid for any just distribution of charges, because the electric field from a distribution is just the sum of the electric fields from the contributions.